Alright, here we go, guys. We are going to pick up right where we left off last time. I believe last time we were talking about organic chemistry or something like that, and we're talking about, it's all about carbon and stuff like that, and we're just going to keep on going. One of the things that we're going to dive into today is like all the different kinds and ways and shapes that well, actually not even, just the very beginning of the ways and shapes that carbon can bond to itself. Because remember, that's kind of like one of the clutch things about carbon is that it can bond to itself to make like different shapes. And so what we try to do in organic chemistry, believe it or not, is we try to capture the shape in the name. So when we say something like methane or propane or butane or butene or butine, we know what the shape is, because I think by now we've established that the shape of a molecule determines what it does and how it behaves. And so the name tries to capture the shape. Because there are just so many different shapes, everybody got together and decided, why don't we come up with a way to like capture the shape in the name so that like you can just say it and we can figure out what the shape is instead of like, I don't know how else you would get the shape across, but there's that. So that's what we're going to do today. And just the very beginning, I believe last time we talked about homologous series, right? The prefix homo meaning same. So these are all like molecules that are very similar in structure, and there's three that we're going to look at today: the alkanes, the alkenes, and the alkynes. Remember that from last time, the three homologous series? Right. Awesome. Table P and table Q, right? The whole like ratio of hydrogen to carbon, that thing. Well, here it is. We're going for it, and we're starting with alkanes. All right. Oh, that was a technical glitch. Sorry. Anyway, we're going to look into alkanes today. Now, alkanes. How do we know that this particular molecule is an alkane? Well, it only has single bonds. I mean that's how, right? So if we have something that has a, what's that at the end? Is that's a suffix? If we have something with the suffix that is alkanes, A-N-E, that means it has only one, or I'm sorry, it has only single bonds, and this is how we tell with this. Only single bonds. What was that? Oh yeah, saturated, right? Because single bonds are saturated. Single bonds are saturated. So that means every carbon is going to have this kind of bond in it, only one at a time. How do we tell? Well, definitely not by memorizing. We're going to use table P and we're going to use table Q, and this is how we're going to do, because memorizing is not what we want to do in this chapter. There's way too much. We're going to like use the charts. So every single time, first thing we need to do is we come here to the molecule and we look at the ratio of carbons to hydrogens. Now here we have 1. So N equals 1. So we would go to table Q and we would just go through them all. 2 times 1 plus 2 is 4. Oh my gosh, look, this follows the pattern of an alkane. You see how that works? It says it right there. So that's how we get the suffix. But how do we know if it's methane, ethane, propane, butane, all that stuff? Well, for that, we need table P. And what we do, I'm going to say this about 1,000 times today, is you count the longest chain or the longest consecutive sequence of carbons, or how many carbons there are. So this guy has 1 carbon. So if you have 1 carbon, the prefix is meth. So this is meth, right? Because it has 1 carbon. And because it is an alkane homologous series, because of the carbon-hydrogen ratio, it ends in ane. Ane, right? That's why this was like in bold, because if it's an alkane, it ends in ane. So that is methane. Let's try this next one. First thing we do. I'm going to do the prefix first this time. If there's 2, there's eth. Eth. And now if we look at the pattern, see 2 carbons. It follows the 2n plus 2 pattern. That's ethane. 3 carbons. Prop. The hydrogen carbon, that's the 2n plus 2, propane. Yeah, propane. You get it? Methane, ethane, propane. And this is what I meant by like each consecutive member in a homologous series increases by 1 carbon. First you have methane, then ethane, then prop, bute, pent, hex, hep, whatever, all the way up. We will not go past decane. That seems like it's enough, you know what I mean? So, like I said, the number of hydrogens equals like 2n plus, whoa, that's 2n plus 2. And the way we do that is we count the longest chain. That's how we find the number. Early morning zoomies. That's how we find the number of carbons. And I want you to remember that for later on when these things start to get really big. Remember, we're just starting out, so they're nice and simple and easy. So let's keep going. Let's name this bad boy right now, shall we? So first thing we're going to do is count up our carbons. I see 1 carbon, and I'm not going to memorize. I'm going to look it up, so that gives me a prefix of meth. No double or triple bonds. That has to be an ane. Right? Because if there's no double triple bonds, you're left with the alkanes. So this is methane. Yeah, it's the simplest hydrocarbon. This is natural gas. When you see little bubbles coming up out of the mud in a pond, that's what this is. It's when things decompose, they often create methane. Fun fact, they believe the permafrost is like packed with methane because it's been frozen up in the North Pole for like ever, and it's melting, and it's a way more intense greenhouse gas than carbon dioxide. But don't worry about it, you'll be fine in the future. Next. All right, let's look at this one. Let's see how many carbons. 1, 2. Wait, am I right? 2 carbons is, oh yeah, 2 carbons is F. Very nice. So this starts with F. No, it's all single, all saturated. That's ane. This is ethane. You guys see how this works? Are you picking up what, like, the pattern here? This next one, I have a feeling you're gonna be able to figure it out. 3 carbons, prop, all single bonds. This is propane. Barbecue gas. We love us some propane up in here. Hank would be proud. All right, so here's the thing. We can go from structure to name, but we also need to go from name to structure. So we are going to need to now draw butane. It's pronounced butane, not butane. So there's the dividing. The prefix is bute, meth, eth, prop, bute. So I will need 4 carbons. 1, 2, 3, 4. And of course they all have to be stuck together with at least 1. And the ending ane means all single bonds. So all single bonds. Now we throw in the hydrogens so that every carbon has, count them up, 4 bonds. This dude has 1 right there. 2, 3, 4. This dude, 1, 2 bonds. So that's 2, 3, 4. That dude right there, he's got 2 bonds. 3, 4. This guy right here, he's got 1 bond. 2, 3. Yeah, there you go. So there's butane. That's the gas in your lighter. So the only difference between propane and butane, it looks like, is, well, 1 carbon. And they do that because they behave a little bit differently. And so, I mean, really similarly, right? They both light on fire very, very conveniently. They're both like a gas that can be compressed into a liquid into a nice little container, but they do behave differently enough that one is really convenient for like a lighter that you can like walk around in your pocket. The other one, maybe you don't want that in your pocket because of the way that it behaves. Next one, pentane. Pent, meth, eth, prop, bute, pent. Or you go up on the table and you look at it and there's 5. So 1, 2, 3, 4, 5. All right, ending in ane. That means it's all hydrogens. But look, you guys gotta. I'm gonna like take like I'm gonna do this for right now because I can't. I don't have time. So I'm just gonna do a dot for every hydrogen. Making sure that every carbon has 4 bonds. Look at that. Isn't that easy? It really is. It actually really is just that easy. Give me a second. All right, sorry about that. Anyway, we were talking about pentane, right? Pentane, and look, it's lighter. It's lighter fuel, like like the stuff you put on your barbecue to light it up, man. It's all the same stuff, right? It all basically does the same thing. It's fire juice. All these things are fire juice, right? Because they all do the same thing. They're really, really good sources of fuel, right? Like octane. We put that in our car. Yeah. You guys get the idea? How they all kind of like behave similarly? All right, moving on. Same, but, whoops. But, basically different are the alkenes, right? So now this one is going to end in an E-N-E, alkene. So, the alkenes, these are going to have at least one double bond between carbons somewhere in the molecule. And unless indicated otherwise, it's only going to be one. We're going to start nice and simple. But these things do the exact same thing as everything else. Let's dig into it. Again, we are not memorizing. You know your P's and Q's. Just look them up, man. You do not have to memorize this. But what we do need to do is know how to find the general formula. Let's start. Two carbons. I'm gonna do first things first. Let's do the prefix first this time. I got all excited last time and did the general formula first. So 2 carbons, F. Okay. Now we'll do the general formula. N is 2. That's 2 times N. That's alkenes. So instead, it's going to be ethene. You dig? Same with this one. This is going to be prop. There's my N. My number of hydrogens is 2N. Propene. Now, propene burns too, but that double bond makes it not just burn, but boy, does it burn way more violently than we would want to have for our barbecue. That would not be the kind of flame that we want. It would be spattered all over the place. So we can't really use propene for our barbecue. Almost exactly the same. The only difference is that propene has one of these double bonds. But if you look there, dude, there's 2 bonds. Remember, chemical bonds store potential energy. So it's not just once, it's twice. It's like double the potential energy. And it's a lot of potential energy once you start getting double and triple bonds. So that's why we typically don't use them as fuel. Let's keep going. Number 4, it's got a prefix of bute. It's pronounced bute. All right. My ratio here, there's my N, that's 2N, that's ene. Butene. It's a beauty. That's too early for this, I'm sorry. All right, yeah, remember, how to find the number of hydrogens. This is just like a reference to the general formula, but you guys seem to you guys get it. Actually, I don't know if you get it or not. You guys are over there and I'm over here. This is stupid. I don't even know what you do or don't get. So if you don't get it, you better like shoot me a message or a text or something. Otherwise, how am I supposed to know if you get it or not? I'm looking at this camera thing, not you. Anyway, count the longest chain. Now, I am going to say this a lot. Count the longest chain. This is a chain. All right, it's a sequence of carbons. Do you see how I'm making a chain? Do you see how it's bent and squiggly? It does, like, this counts as a chain. So does this. That change can be squiggly, right? But if you look, it goes down. All right, you can have a squiggly chain, or you can have a straight chain. It doesn't really matter, right? A chain is a chain. It's a consecutive sequence of carbons. That's what really counts here. Let's go on to how we name some things. Here we go. But no, now we go. All right, let's check out this one. 2 carbons. And look, there's a double bond, so that's going to be ene. This is called ethene. You have never dealt with ethene, but I guarantee you've seen the sorry. But I guarantee you've seen products of ethene, right? Your number 2 plastics or your number 4 plastics. They were they're made with some of this stuff. Right? And they're just like all stuck together and stuck together and stuck together, and that's how we make a plastic. It's like a polymer or like a big web of molecules all like sort of stuck together like spaghetti. You know what I mean? And then bam, you got yourself like plastic. You put milk in it and orange juice and stuff. All right, next one, 3 carbons. And look, do you see how these are like different? I want you to get used to seeing these in lots of different ways, because there's like a gajillion different ways to draw these things, and there's no one standardized way. So I'm going to come up with a bunch of different ways, and you're going to manage, because I know you can. So here we go. We've got 1, 2, 3 carbons, prop. We've got our double bond right there, that's ene, and this is propene. Way more reactive than propane, but there it is, propene. We use this for all kinds of stuff in chemical reactions and whatnot, but there it is, there's propene. The next one, 4 carbons. We've got 1, 2, 3, 4 carbons. That propute. Right here is my double bond. That's going to end in ene. Butene. Beauty. Oh, one other thing. You see there, this guy, this is 1 butene, right? Just to like be specific, because we actually have to be that specific. And the reason why we're going to start calling this 1 butene is because this double bond right now, right? It is in the first bond position. It's way out at the end, right? So the number 1 tells us where it is, and we really need to know that, because if the double bond is here, way at the end, that makes it really, really reactive. In other words, it'll react like crazy. However, if the double bond was here, for pretend, right, then this would be in bond position number 2. So let me get a different color here. Let's go gold, get a sparkle gold. This is bond position 1. This is bond position 2. So if our double bond was here in bond position 2, it would be a little more stable. So at the end, very, very, very reactive, very, very unstable. If it's in the middle, it's a little more stable. So the closer into the middle these double and triple bonds get, the more stable your molecule can be. And that is really important, because I need to know that to be able to handle it safely. Also, if I react it with the bond here, this is where the reacting is going to happen. I'm going to get stuff stuck way out at the end. But if I want it to be in the middle, then I would need something with the double bond. So all the things that I would stick to it would be in here. And that is how we like build these like synthetic molecules, right? That's how we make medicine. Like we don't, like ibuprofen and acetaminophen, man, that is made in like a lab somewhere. And we know how to do it because we know exactly where all the things are going to stick by knowing where all the double and triple bonds and whatnot are. You guys get what I'm saying? Now let's check out this guy. Very, very similar, yet very, very different. All right, 4 carbons. This is going to be bute. Double bond, ene, butene. This is a problem. See how this is butene? See how that's butene? Butene, man, you can't have 2 things with the same name, remember? So I'm going to come up here and I'm going to correct this. Remember, this is 1 butene. This is 2 butene, because my double bond right here, it's not at the end. See, this is bond position 1, bond position 2, bond position 3. So this is going to have to be, what am I doing? I am messing up. I messed up. Can you believe I made a mistake? Oh man, I can't believe it's only been I can't believe that's my first one. Like, I've been awake for more than an hour, and that's my first. Hey man, good for me. 1 mistake so far. Okay, 2. This will be 2 butene. Why? Dude, I gotta know where that double bond is, so I know how to handle this. 1, so I know how to handle it safely, and 2, so I know how it's gonna react and what it's gonna produce. You get it? So with these 2 things, this guy, I'm pointing at the screen, this guy right here and this little fella down here, while they look really similar, they are not the same. okay? Because they will behave differently. And it's important for us to capture that different structure in the name because structure is function. Does that make sense? And also, you want to count so the bond position has the lowest possible number. All right? So this one's pretty easy. There's only one choice. But let's come up here to our other example. If you notice, I chose counting from here, 1, 2, 3. I could have chosen to go like this. Bond position 1, bond position 2, bond position 3, but that would have given this a number 3. And I don't want to do that. I want to start so that the bond, no, see, wrong. I want to start so that this double bond has the lowest number possible. And the reason being is I want to know how close it is to the end of the chain. Because remember, the closer it is to the end of the chain, the more highly reactive it is. So I want to know, man, do I need to have a blast shield on? Do I need to have it in like a special container? Or am I like, okay? You get what I'm saying? So when we choose bond position, we're just going to give it a number. And you choose the number so that it's like the lowest possible numbers. Like as far as you like, if you start counting from the left or if you start counting from the right, you start counting so that the bond has the lowest number possible. If that makes sense. We're going to do this about 100 times so that it will. And this gives us words. Isomers. Man, isomers. If you guys, man, I'm going to see if I can find something about thalidomide. I wish I had time to tell you about thalidomide. Boy, was that a thing. So isomers. These are molecules that have the exact same number of atoms and molecules, but they have a different shape. It's like you make something out of 50 Legos, you break it apart, you make something completely different out of 50 Legos. Right? The exact same number of like bits and pieces. So this one might have 20 carbons and 50 hydrogens. You break it apart, whole new shape, 20 carbons, 50 hydrogens, whole new shape. And if it's a completely new shape, it's like a completely new thing, right? Like if you take a key with exactly 3 grams of brass, you shape it one way, it's your house key. Shape it another way, it's key to your tractor. Looking at a tractor out there. Yeah, you know what I mean? So isomers are molecules that share the same molecular formula, in other words, the same number of stuff, but different structural formulas, right? This is shape. And therefore function. And boy, can the function be different with even a very small change in shape. Holy cow. There's like, I cannot emphasize that enough, especially when you get into organic chemistry and these molecules of of life and like things that we put into our body, man. Like the difference between methamphetamine and like allergy medicine is small, right? I mean, that's how they make meth. That's why Sudafed is behind the counter at the pharmacy, because the difference between Sudafed and methamphetamines is about that much. It's almost nothing. It's so easy to. Meth heads can change Sudafed into methamphetamines. It's not a hard thing. Meth heads can do it. So the difference is teeny, and look at the profound difference of like sniffles from like allergies and meth. All right, that was depressing, but let's keep on going because chemistry is chemistry. It don't matter if you're sad or not. I hope you're not so sad. So let's start drawing some stuff. Okay, so these guys are going to be a little bit different because it's going to have a double bond. See, these are going to all end in -ine, so they're all going to have a double bond. So we're going to have to be careful about where that is. Just like the alkanes with one extra layer. So prefix of but is 4. So I'm going to go meth, eth, prop, but. But there's -ene, so I've got a double bond. Well, where could that double bond possibly be? I don't even. Oh, yes, I do know. It's right here. It's on bond position 1. And since I'm going to be fancy, I'm going to make it over here. All right? I'm just counting from the right instead of the left. And it doesn't matter because look, what side is my thumb on? Okay, now what side is it on? See, this is a 2-dimensional drawing of a 3-dimensional object, which is often very challenging to know that this and this are the same thing. It's just like there it's this on this side, there it's like on that side. You get what I'm saying? So I just chose to number my bond positions from the right. 1 butene, and then we're gonna sprinkle this in with a whole bunch of hydrogens. I'm gonna use dots to save time. And this one has 2, 3, 4. This guy has 3, so he only gets 1 hydrogen. 1, 2, 3, 4. This guy's 1, 2, 3, 4. That was easy peasy lemon squeezy. Let's try another one. Let's try 2-butene. All right. Prefix but, meth, eth, prop, but. Now this one says 2-butene, so I'm gonna have to go in 2. Bond position 1, bond position 2. That's where my double bond is gonna be. And now I'm gonna have to cover it with hydrogens. So this guy has 1, 2, 3, 4. This carbon has 3, so it only gets 1 hydrogen. This carbon has 3, so it only gets 1 hydrogen. This carbon has 1 bond, so he gets 1, 2, 3. You guys picking up how this works? Let's try this one. Octene. Oct. 8. So meth, eth, prop, but, pent, hept, oct. Okay. Octene, but here's my ene. Where, oh where could my double bond be? Where, oh where could my double bond be? Oh, it's over right there. It's at the... I'm not doing it. Okay, so bond position 3. So really, there are 2 answers here. There are 2 ways to draw this. I could do bond position 1, bond position 2. I could put it here. Right, that's the 3rd bond position. Or I could do it bond position 1. Bond position. Or I could put it there, but you'll have to choose. It's going to be like one or the other. It's not going to be both. I'm going to go for right there, just because I kind of feel like it is why. Okay, so then we add hydrogens so that every carbon has 3 bonds. And let's see what 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. Just gonna rip through this so you don't have to watch a 3-hour video. There you go. That's easy. Oh, gee. What's that? Dioctane? 1, 2, dioctane? Alright, that's just... Guys, it's the same exact thing. But with, once again, 1 extra layer. Di... Oh, that's not going to work out for me right here, guys. Give me a second. The prefix di is not what you might want to do for having to watch so many chemistry videos, but it actually means 2, right? Mono, di, tri, tetra, that thing. The oct, that means 8. Ene tells us that there's a double bond in there. So, if this is octene, or 3-octene, 1, 2 dioctane is going to look pretty similar. So, oct is 8. 1, 2, 3, 4, 5, 6, 7, 8. But it's got some double bonds up in here. How many double bonds does it have? Double. So there's 2. There's 2 double bonds. Where? Where could they be? There's like all these bond positions. How am I going to... Oh. So this is doubling up. This is what we call redundancy to make sure people don't mess up. Bond position 1, bond position 2. So bond position 1, bond position 2. Di. Remember there's 2, so double check, make sure there's 2. Octene. So there's a double bond here, there's a double bond here. The rest all get hydrogens. So let's review really quick. 1, 2, that's your bond position. So it looks like there's going to be 2 double bonds. Di, yep, prefix di. That means there are going to be 2 double bonds. Oct, ene. Oct tells us the number of carbons. Ene tells us what kind of bonds we're looking at. So 2 bonds, 3, 4. 1, 2, 3, 4. Man, that guy gets 0 hydrogens. This guy 1, 2, 3, 4. 1, 2, 1, 2, 1. 2, 1, 2, 1, 2, 3. Done. Sort of. there's more. Whoa, whoa, hold on. Whoa. There we go. Now there's going to be more. Dude, we're going to rip through this so fast because the alkynes are exactly like the alkenes with one exception. It's an ine. So there's going to be at least one triple bond up in this JOM. It's going to work the exact same way. First, we look at the number of carbons. We come over here and get our prefix. This is F. Excuse me. Then we look at our the ratio of carbons to hydrogens. So if n equals 2, it's going to be 2 times 2 minus 2. So 2 times 2 is 4. 4 minus 2 equals 2. Oh my gosh, look, we're at the alkynes. So this is F-Y-N-E, ethyne. 3 carbons, meth, eth, prop. 3 times 2 is 6. Let's see. Oh, it's following this pattern. 2n minus 2, so 6, 9, all right. You see how this is following the exact same pattern? 4, what is that? I can't even remember. Oh yeah, bute. Same as before, count the longest chain. If it follows this pattern, you're into butyne. So let's go through. 4 carbons, meth, eth, prop, bute. There's a triple bond. This is butyne. Technically, this is going to be 1, 2 butyne. Remember? Because you got to tell us where that is. Now, double bonds have a lot of energy. Triple bonds are like flat out explosive. Like literally. They're like, it's a little bit stupid how explosive these things are. Typically, it's actually not terribly common to find anything with any carbons with triple bonds because there is so much energy packed into that triple bond. Like all these electrons are packed into that one space. It's actually explosive. I would not want to walk around with a container with this stuff. But what we do is we make it and then use it as soon as we make it so that, we have it for our reactions. Draw propyne. Okay. All right, let's do this. Let's not be scared. Prop. If we look at our reference chart, this means 4. Ine means triple bond. So it'll be meth, eth, prop. Okay, wait. Whoa, I did that wrong. Wait, let me double check here. I'm not sure. Prop. Oh man, I was wrong. I'm glad I checked. It's twice in one day. Oh my gosh. All right, 3. Meth, eth, prop. And it says ine, so I'll just put my triple bond there, and you splatter in your hydrogens to get 4. So this guy already has 3. There's my H. This guy has 1, 2, 3, 4. He gets none. 1, 2, 3 on that guy, and there's his 4th bond. Look, everybody's happy. Woot, woot. Very nice. All right, let's check the next one. 2. That tells me where. Pent. Alright, I'm not going with my brain on this one. I'm not going to trust my brain. Let's do this. Pent 5. Okay, so I'm going to need 5 carbons. 1, 2, 3, 4, 5. And it says ine. There's my triple bond. I need my trips. But where am I going to put it? I've got 1, 2, 3, 4 bond positions. Right there. 1, 2. Now we're going to splatter in our hydrogens. This guy's 1, 2, 3, 4. That guy's got 4. That guy's got 4. Yeah, we're good. Get it? Same exact thing, only because the suffix is ine, we know it's a triple bond. At least that's what it is on paper. If it was real life, I would actually be kind of scared to handle this stuff. It would have to be in very small quantities, and I would like to have a big glove and a blast shield in front of me, because. Or not. Maybe I would just need a lighter, you know what I mean? Because this stuff would evaporate, make a big cloud. You ever see those guys that try to light a big bonfire of gasoline and it explodes in their face because they're too dumb and they never paid attention in chemistry class and they forgot that liquids don't burn but the vapors do? You learned that when we talked about pyrolysis, remember? Remember that guy with the big beard and the cupcake? So they poured all the gasoline everywhere. The gasoline vaporized and went to light it, but they lit the vapors and everything exploded. But that's just 8 single bonds, man. You put that triple bond in there, there's not going to be a video of it because it's going to be like evidence for, you know, the coroner. Anyway, boy, that was a tangent. It's like I'm right back in the classroom. Let's name this one. What is the name of this thing? All right, so first thing we're going to do is count the longest chain. First thing we're going to do is count the longest chain. 1, 2, 3, 4. Meth, eth, prop, bute. So I'm going to call this bute. Triple bond, ein, butane. But where, right? Where is that triple bond? Bond position 1, bond position 2, bond position 3, 3-butane. Easy, right? So how did I just name that? I counted the longest sequence of carbons. That gave me like my prefix, right? So I got that from the number of carbons. This, the suffix, that came from bond type. Yeah. And then finally, this one was where. Where is it? So these things tend to get built, we build the name backwards. We start typically on the right and then we move over to the left. So we start here, we move there. It's how we build it. And then we read it left to right, because why wouldn't we do that? All right, so here's what I need us to be able to do. We need to be able to go from name to molecular formula to structural formula to condensed structural formula. Do you remember this way from the beginning? So here's what we're going to do. We're going to do a couple of these together here. 2-butene. Whoa, I don't even know how it happened there. Bute. You know, computers. 2-butene. So bute, meth, eth, prop, bute. So I can't do the molecular formula. Well, wait, yes I can. I can do the molecular formula. Remember, there's that whole general formula thing. If it's an ene, it's an alkene. So if it's bute, meth, eth, prop, bute. So I've got, I have no idea what's happening, but that's straight trippy, right? So I'll have 4 carbons. And if it's an ene, the hydrogen is just twice as many. How did I figure that out? Remember, on table Q, the general formula for the alkenes is 2N. So the structural formula, I don't know if this is going to let me do it. I'm going to go 1, 2, 3, 4. Double bond. Where is it? It's in spot number 2. And then hydrogens. I'm using dots for hydrogens just to go fast because we don't have time. Now condensed structural formula. Remember, this is where you just write the carbon, then how many hydrogens are after it. So this was the name, 2-butene. The ene tells us that we're in the alkenes. The bute tells us how many carbons. So C4 because of bute, and then H8 because of ene, right? Went to the general formula, that's how. And then I know that I've got 4 carbons, 1, 2, 3, 4. I've got a double bond in the second position, right there, and I should have 8. 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. That's my structural formula. That's the actual shape of the thing, and now we're going to do condensed structural. This is what we use more in like sentences and stuff. So here's how we do. First carbon. What's attached to the first carbon? That's it. Second carbon. What's attached to it? 1 hydrogen. Third carbon. What's attached to your third carbon? 1 hydrogen. Fourth carbon. What's attached to that? 3 hydrogens. Boom. Done. That's it. Let's do the next one. All right, so this one we're given molecular formula. I don't know if I want to go to the name just yet, but we can do structural formula, I'll bet. So C7H16. I don't know what's going on with this silliness. So 1, 2, 3, 4, 5, 6, 7. Now I'm going to go to the general formula on table Q. Is it 2n plus 2? Is it 2n? Is it 2n minus 2? This looks like 2n plus 2. So it must be... Hey, what's up? Do you need my help or something? Hey guys, you're going to have to time out for a second. I'll be back. Okay, I'm back. So where were we? Oh yeah, C7H16. There's my 7 carbons. This looks like 2n plus 2, so it's going to have all single bonds. So my hydrogens are just going to be like boop, 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 boop. There. What are we going to name this? Propute. Wait, I don't even remember. I don't remember anything yet. Oh, yes I do. It's hept. Hept. The prefix for 7 is hept. And since it's all single bonds, heptane. So, condensed structural formula. Here's how we do. The first carbon has 3 hydrogens. Second has 2. Third, 4, 5, 6. And the last one, oops, like that. I don't want to do that one. Let's do this one because I'm running out of time. My daughter just made me breakfast, so I'm ready to get out of here. You know what I'm saying? All right, so let's do this one. 2-pentyne. The molecular formula. Think I can do that from just this? Yes, because pent, that means I have 5. This is terrible. If it's an ene, that means I'm in the alkene, so it's 2n. There, done. Structural formula. I've got 5. 1, 2, 3, 4, 5. I know that I've got a double bond. Boop, look, I did that. Right? And where is it? Bond position 2. So I'll put my double bond right there. Throw in the hydrogen so everybody has 4. 1, 2, 3, 4. This guy's 3. There's 4. 3. There's 4. Here. Done. Condensed structural. My first carbon has 3 hydrogens. Second carbon has 1. Third carbon has 1. Fourth carbon has 2. Fifth carbon has 3. Right? So that is that guy. This is this guy. This. You guys see how this works? I'm gonna go down. Yeah, you feel how this works? I hope you're getting it. And what I really want to say again is that these are, man, you have to have, like, don't memorize these things. I mean, it's too much to memorize. Who wants to memorize? So just get out your reference table, keep them in front of you. Remember, single bonds are saturated. Double and triple bonds, these are unsaturated, and these are your prefixes. That is it for today. Do you think that's enough for one day? I hope so, because... Wait, there's no homework. Wait, there can't be no homework. There can't be no homework. There can't be no